This is a question based on AQA A-level Chemistry. It is from the required practical assessments in paper 3, and this one is focused on RPA5. Going to recommend you pause, have a go at the question for yourself, and then review your answers. So here is part A. And finishing off with parts B and C. Okay, so let's take a look at what we need to do here. We've got propanone being made by reacting propan-2-ol with an excess of acidified K2Cr2O7. The propanone is then removed from the reaction mixture by distillation. We've got a diagram showing the apparatus set up by a student to make propanone. We have got suitable clamps used to hold all apparatus firmly in place. Even though they're not shown on the diagram, we know they are there. So you have got to come up with 3 problems with the apparatus that are set up in the figure above. You need to identify the problem, say what issue it would cause, and suggest how the problem can be solved. This is, as you can see from the mark allocation, a 6 marker, which means we're going to break it down into 3 stages. You need to get the majority of each stage correct if you're going to get into level 3 to get to those 6 marks. So let's break down the 3 stages. It's actually quite easy on here. We're going to look at each of the problems and we're going to get the information about them. So stage 1. There are no anti-bumping granules that have been added. We need to include those as part of it. They've not been labelled on the diagram. We can't see any images of them. So we can start to deal with that. Why do we need the anti-bumping granules? Well, they actually prevent the formation of larger bubbles or lead to the creation of smaller bubbles. And that means you're not going to get the apparatus moving around, bumping around, hence the name. And if that's the case, we have now fixed that problem. That allows us to move to stage 2. Now with stage 2, the system is not closed. It's open at the top, and we don't do that here. If we're heating something where we are oxidizing a secondary alcohol to a ketone, we know that ketones are volatile. So actually, if I produce them, they would vaporize and they would escape out of the top. So what we would need to do is use a bung, potentially a thermometer as well, so that we're sealing that, and therefore there are no more risks of that propanone escaping. So that's going to allow us to collect it, which is what we're wanting to do at the end of this apparatus, as we can see in the diagram. For stage 3, we have got water flowing in the wrong direction. A really common error when people set this up, actually, but we must remember the order that it goes in, and you will always have the water going in at the farthest end of the condenser. And that's because otherwise the condenser might not be cool enough. If cold water goes in where your vapour is hottest, the water might be warmed up rather than the vapour cooled down. And if that were the case, the product might not condense. It might vaporize and escape rather than get collected in the test tube. So there are my 3 stages. They are the 3 things that you need to be able to explain to get to level 3 and to get to 6 marks. Let's move on and look at the rest of the question. We've got another student completing the experiment using the apparatus, which is set up correctly. 2 cm cubed of propan-2-ol, an excess of acidified K2Cr2O7, and they got 0.954 grams of propanone. Calculate percentage yield of propanone in this experiment and give your answer to an appropriate number of significant figures. So let's start with what we can work out. We want to know the mass of propan-2-ol. And the propan-2-ol, well, we've got a density and we've got a volume. I've highlighted those so we can see them. You've got to pick through this calculation, this question, to find the data to do these calculations. That takes us to 1.572 grams. If I've got the mass of propan-2-ol, I can work out the moles of propan-2-ol using M over MR. Now, we've not been provided with atomic masses or molecular masses, but you have a periodic table. You can work them out. So we're going to take our mass, 1.572, and we divide by the MR of propan-2-ol, which is 60. Once we've done that, we get to 0.0262 moles. And we can look at the expected mass of propanone that we would expect. Now, for this, we are going to take N times MR. My number of moles is 0.0262. For this, we've got to appreciate that it's a 1-to-1 mole ratio of propan-2-ol to propanone. This time we're multiplying by the MR of propanone, which is 58 rather than 60. And that takes us to a value of 1.52 grams. So that's how much we should have made if everything had gone exactly as the theory tells us. But percentage yield is what's the actual mass we got divided by maximum theoretical mass, multiply that by 100. So I've got 0.954, which is what we actually obtained, divide by 0.954 that we actually obtained, divided by 1.52 that we should have obtained, to get a percentage multiplied by 100, and we get to an answer of 63%. And it has to be to two significant figures. If you go through, some of the data that we've been given is only two sig figs, so we can't go any more than that. Got to be mindful of that when answering questions like this. Moving on to part C, molecules of propan-2-ol and propanone each contain 3 carbon atoms. Complete the table below to suggest the shape and the bond angle around the central C atom in a molecule of each compound. Well, in propan-2-ol, the central carbon has got 2 CH3s coming off it, a hydrogen and an OH. It's got 4 bonds. That means it's based on tetrahedral. But in propanone, I've got 2 CH3s and a C double bond O. The double bond in shapes of molecules behaves as a single bond would. So 3 bonds, 3 bonding pairs. That means it's trigonal planar. And then right back to the bonding topic, it's simply remembering tetrahedral is 109.5 degrees and trigonal planar is 120. Finally, explanation of why propanone has a lower boiling point than propan-2-ol. Well, let's start by drawing those out. You can see here that we have got hydrogen bonding in propan-2-ol. We don't have hydrogen bonding in the other one. We have got dipole-dipole. And we know that hydrogen bonding is stronger than dipole-dipole. They are stronger intermolecular forces. And so taking a look at identifying the strongest type of intermolecular force in each, there's 2 marks. Recognizing that hydrogen bonding is stronger, there is your 3rd mark. That takes us to the end of this question. Thank you for listening and goodbye.